Einstein's three papers of 1905, the three great papers, there's a fourth, of course, the E equals mc squared, but that Einstein saw as following from his thinking about relativity. But his basic three papers, relativity, Brownian motion, the motion of suspended particles like a smoke particle or a small particle in liquid, and then the idea that light was itself particulate, that there were actually units of light, photons, had three different fates. The relativity paper was almost unreadable to people because of its philosophically structured, inverted order. It seemed to people somewhat incomprehensible why you would begin with force-free motion. It seemed to them somewhat incomprehensible why you'd begin with these elementary discussions of measuring space with rulers and clocks and signals back and forth between clocks. They didn't really get it in 1905. Very few people seized it even enough to violently object. It took a couple of years and the intervention of Minkowski and others to present it in a form that grabbed people's attention, polarizing the community somewhat, but leading eventually to its understanding and acceptance. Brownian motion was rather different. Brownian motion, the motion of these suspended particles, was very understandable to people, and Einstein's work led to almost immediate reception and acclaim. The photon paper people thought they understood, and they hated it, as Henri Poincaré did. So incomprehension, acclaim, and revolt against it were the fates of these three papers. But let's focus on the Brownian motion paper because it too begins with the same kind of asymmetric reasoning that Einstein had brought forward in his relativity paper. Brownian motion as a phenomenon goes back a long way. Before 1828, the random motion of suspended particles, like pollen, was thought to be a form of life. In that year, the English botanist Robert Brown showed that he could obtain the same motion through suspended pieces of glass, metal, and rocks. So then people had to quickly regroup because it clearly wasn't living. People speculated about maybe the heat of the light used to illuminate the sample of liquid was making little convection currents and moving these particles around. Einstein began this way. It will be shown in this paper that, according to the molecular kinetic theory of heat, the idea that heat is just the motion of atoms and molecules, bodies of microscopically visible size suspended in liquids must, as a result of these thermal motions, perform motions of such magnitude that these motions can easily be detected by a microscope. It is possible that the motions are identical with the so-called Brownian molecular motion. So Einstein is saying, let's focus on something you could actually see with a microscope. He then continues, if it is really possible to observe the motion to be discussed here, along with the laws it is expected to obey, then classical thermodynamics can no longer be viewed as strictly valid even from microscopically distinguishable spaces, and an exact determination of the real size of atoms becomes possible. Conversely, if the prediction of this motion were to be proved wrong, this fact would provide a weighty argument against the molecular kinetic conception of heat. Well, the molecular conception of heat is that heat is nothing other than the motion of these particles. And Einstein was saying, this is a test of the real structure of these atoms and molecules, not a useful fiction that could be used to reproduce the idea of heat as a kind of continuous fluid, but rather a test. These atoms and molecules have real sizes that can be measured, and we can prove their existence if what he says in this paper is true. If not, then you've got a good argument against their reality. On the one side, Einstein says, lies the classical theory of thermodynamics with its determinate outcomes and absolute predictions. The idea of entropy, the idea of a measure of disorder, quantity in thermodynamics that seemed to always increase. Always, not most of the time, always. That's how Max Planck interpreted it, for example. On the other side stood a statistical mechanics that Ludwig Boltzmann had advocated, in which case entropy was only most of the time increasing. It was possible that strange things could happen. All the air in the room could suddenly go over to the garbage can and sit there, leaving the rest of the room in a vacuum. It was very, very unlikely, but there was always the possibility that order could come out of disorder rather than just constantly increasing disorder. Boltzmann's view was that the properties of thermodynamics were only approximate. Brownian motion put the two accounts to the test when Einstein focused on the one place where classical thermodynamics and the molecular theory of heat disagreed, and that was in fluctuations, like the sudden motion of, say, a red dye all back into a little lump rather than its constant diffusion. Fluctuations were possible in the Boltzmann account, and Einstein used that strategy to reason about Brownian motion. So how do you think about molecules that were, say, 10 to the minus 8 centimeters, 100 millionth of a centimeter, hitting suspended particles that were only, say, a 10,000th of a centimeter? Einstein was essentially saying that it was like millions of randomly flying penguins hitting an iceberg. Mostly they'd sort of be equally distributed on the different sides of the iceberg, and the iceberg would sit still. But it was possible that once in a while, lots of penguins would hit, say, from the right, and very few from the left, and the iceberg would be moved. That idea that there would be fluctuations led to this phenomenon that he could actually calculate. And he did. Einstein said, if you had, say, water at 17 degrees and particles of about 1,000th of a millimeter, you obtain the mean displacement in 1 minute to be about 6 microns, 6 millionths of a meter. Again, he starts with this clash between the continuum theory of thermodynamics and the discrete theory of molecular motion as being what constitutes heat, focuses on a principle to look at this, that we can really just treat the idea of these collisions as fluctuations, and then predicts a consequence. Well, people loved this paper. Poincaré in 1908 said, "The atomic hypothesis has recently acquired enough credence to cease being a mere hypothesis. Atoms are no longer just a useful fiction. We can rightly claim to see them, since we can actually count them." How do you count them? You use Einstein's prediction of this Brownian motion to actually deduce something about the real atoms and molecules that are hitting them, and that through their fluctuations are leading to the motion of that suspended particle. Wilhelm Ostwald, who had hoped that everything in the world could be explained through energy alone, said in 1909, "I have convinced myself that we have recently come into possession of experimental proof of the discrete or grainy nature of matter, for which the atomic hypothesis had vainly sought for centuries, even millennia." They had very different philosophies, Ostwald and Poincaré, but they saw in Einstein's account of molecular motion and Brownian motion proof that atoms and molecules were real with definite sizes. You could count them.